All right, let's get right into it. We're going to tackle a really fascinating puzzle in aviation called the altitude illusion. Now, this is one of those concepts that might seem a little backwards at first, but trust me, it's absolutely essential for any pilot to wrap their head around.
So let me just throw this question at you right at the start. Imagine you're flying. Your altimeter says you're at a perfectly fine 8,000 feet, but the plane just feels sluggish. You know? It's not climbing the way it should. The engine feels like it's gasping for air. It honestly feels like you're way, way higher, maybe at 12,000 feet. So what on earth is going on here?
Well, the answer, and this is the cool part, has almost nothing to do with the plane's mechanics. It's all about the air, the atmosphere that the plane is flying through. You see, an aircraft's performance is totally, fundamentally tied to the air itself, not just the number you see on the altimeter.
The whole idea really boils down to something pretty simple. Dense air versus thin air. Just think of it like this. Dense air is thick. It's packed with air molecules. It gives the aircraft more stuff to work with. But thin air? Well, the molecules are all spread out, and the plane just has less to grab onto to do its job.
And when I say it affects the plane's job, I mean it affects everything. The wings need those molecules to generate lift. The propeller needs to take a good bite of the air to create thrust. And maybe most importantly, the engine needs to suck in lots of air to mix with fuel to generate power. So less air means less lift, less thrust, less power, less performance all around. It's that simple.
So what are the culprits? What actually makes the air thin? Well, there are four big ones. The obvious one is high altitude. The higher you go, the thinner the air. But hot temperatures do it too. They make the air molecules expand and spread out. A low-pressure weather system does the same thing, and here's the one that surprises people. High humidity. Water vapor is actually lighter than air, so it displaces those crucial air molecules. All of these are bad news for performance.
Okay, so with all these things changing all the time, temperature, pressure, humidity, how can a pilot ever reliably predict how their plane will perform? Well, aviation came up with a really clever solution. They just created a perfect standardized day, a totally unchanging yardstick that we can measure the real world against.
And here it is. This is aviation's perfect day. At sea level, the standard day is officially a nice, cool 15 degrees Celsius, that's 59 Fahrenheit, with a barometric pressure of exactly 29.92 inches of mercury. This is the gold standard. This is the baseline for literally everything.
And I really want to stress this point. This isn't just some fun fact for a trivia night. This is the absolute foundation for how we design, test, and calculate aircraft performance. Every single performance chart in every flight manual is based on the numbers from this perfect standard day. But of course, the real world is almost never perfect, right? It's rarely 15 degrees and 29.92. So pilots need a way to correct for reality. And this is where we get to the idea of a feels-like altitude, the altitude that the aircraft thinks it's at, performance-wise. The very first step in this correction is something called pressure altitude. All you do is take your actual altitude off the ground and adjust it for any pressure that isn't that perfect 29.92. This gives you the first piece of the puzzle, telling you what altitude the plane feels based only on pressure. And then we get to the final, and honestly, the most important number, density altitude. You take that pressure altitude we just figured out, and you correct it again, but this time for any non-standard temperature. This number is the money shot. This is what tells a pilot exactly how the plane is going to perform right here, right now. It is the true feels-like altitude. And this lays it out perfectly. It's just a simple, logical flow. You start with your actual elevation at the airport, you apply that pressure correction, which gives you pressure altitude, then you take that number and apply the temperature correction, and voila, you get your density altitude. It's just a two-step process. Okay, that's enough theory. I think it's time we actually run the numbers on a real-world problem to see exactly how this works in practice. So here's our situation. We're at an airport with a field elevation of 3,894 feet. It's a really cold day out, only 20 degrees Fahrenheit, and we've got a high-pressure system sitting over us, so the altimeter setting is 30.35 inches of mercury. First things first, we've got to correct for that high pressure. So we look at a standard conversion chart, but our exact pressure of 30.35 isn't on there. No problem. We just have to do something called interpolation, which is really just a fancy way of saying we'll find the value that's right in the middle of the two closest numbers on the chart.
So after doing that quick little bit of math, we get our pressure conversion factor. It's negative 394 feet. And that negative number is a big clue. It's telling us that the high pressure today is actually going to help us. It's going to make the plane perform like it's lower than it really is.
Now we just plug it in. We take our actual field elevation, 3,894 feet. We add our negative 394 conversion factor, which is the same as subtracting, right? And we get our pressure altitude, a nice round 3,500 feet. See, we're halfway there.
Okay, final step. We pull out a different chart for density altitude. We go down the side to find our new pressure altitude of 3,500 feet. Then we go across the top to find our super cold temperature of 20 degrees Fahrenheit, and we see right where those two lines meet.
And there it is. Our final density altitude is 2,000 feet. Now, stop and think about that for a second. The plane is physically sitting on a runway at almost 4,000 feet, but because it's so cold and the pressure is so high, it's going to perform as if it's taking off from an airport at only 2,000 feet. The performance is going to be fantastic today.
So why do we bother with all this math? You might be thinking, okay, that's a neat trick. But this is not an academic exercise. This single number has immediate, critical consequences for a pilot in the cockpit. It's all about safety.
This chart just says it all, doesn't it? On the left, you've got where the plane actually is. On the right, that's the altitude the plane thinks it's at, performance-wise. Now today, that gap works in our favor, but imagine a hot, low-pressure day. That feels like bar could be thousands of feet higher than the true altitude, and that is a recipe for disaster.
And that really is the bottom line. Density altitude isn't just some number you memorize to pass a test. It is a critical safety tool. It tells a pilot, do I have enough runway to get off the ground? Am I going to be able to outclimb those trees at the end of the runway? Ignoring this number can be, and sadly has been, fatal.
It's such a powerful concept, right? It's all about aligning our perception with cold, hard reality. And it makes you wonder, this idea of a feels-like condition, it applies to so much more than just aviation. It really begs the question, what's the biggest gap you've ever seen between what something is and what it actually feels like?